Okay, hello everyone. Hope you're all doing well. Okay, let's start. Um, Nick, let's do some, problem solving from quantum state, quantum basis. Remember, guys, learning any new topic, it's always challenging. So, the more you challenge yourself, try to solve some problems, the better you would understand it. And of course, this process, it's going to be painful. By the way, what you just saw on the right side of the screen is a palette. Under the palettes, you can see, after installing, Quantum Packlet, you should be able to see that palette. Uh, it helps you, some of you asked, for how you can easily see the patterns for, relevant definitions. As you can see, we added, some, we are planning to extend that. But if you click on any of them, how to do it, create a quantum state, let's get one example. Like you see, this is zero state, or the measurement operator, second operator. So and you can see the results. Okay. Um, Another interesting button, on that palette is reinstall the Packlet. So it's basically, I know some of you, you had some issues, but if you just click on that, you can basically reinstall the Packlet every time, making sure that you are using the very latest version. Uh, okay.
It's equivalent to this command over here.
Yeah. Anyhow, let's go through our problem. So let's go with the first one. Let's see what we have. Create a random two-dimensional pure state.
Should I do it?
Yeah. Let's see,
I wonder.
so it's clear, it's a, quantum state. And this time, Nick is going with the, the building names that we have. So it gives you a random pure state. Remember, whenever no dimension is given, automatically we would assume, it's happening in 2D. Another approach is just what Nick is showing you here. You can go with the generating your own vector. So what's happening in the second example is that Nick is creating two random complex numbers, and you can inject it as an amplitude. So the second option, you may it may give you some headache, because it's not normal. As you can see, Nick is showing you the normalization factor, but the building it returns a normalized state. Okay, so both ways you can create a pure state. The main benefit of using random pure is that you can easily generalize it in any dimension. Okay, so you can easily go the 2, 3, increasing the number of states, whatever you want to do. Okay, the next step, so let's say that you have your random. By the way, as we are discussing, you feel free to type your questions, and we would address them. So look at the examples. The first one is a random pure state in 3 dimensions. The second one is a random pure state of a composite system. The first system has the dimension 2. The second system has the dimension 3. Okay, so random pure helps you to easily create random pure state in any dimension. For any when we have a qubit 2-dimensional quantum system, you can directly visualize the Bloch vector. So let's just create a random pure state in 2D, and let's visualize. So it's Bloch plot, that's the property that you can ask. And that's basically your random pure state in Bloch sphere. And of course, the vector, the red one, the Bloch vector that you see there, you can either get the spherical coordinate of that vector, or you can easily extract the Cartesian coordinate. So for the one of them, you have to ask, let's go the next one, spherical coordinate.
Spherical.
So that's the spherical coordinate of that one. And likewise, you can go with Cartesian coordinates.
Hey, Nick, would you mind trying to go to 150 magnification? It is looking a little small.
Sure. Maybe,
There.
well, I can do even 200 all the way. Oh, it's too
Okay.
big.
Yeah, I think 150 is going to do it.
150
Thank
is
you very
good.
much.
Okay. Okay. Now, like, one interesting, like, the feature that you guys can do is, I'm sure you already noticed that, but like, it's very useful going from one basis to another basis, because whenever basis is not given, like all these cases, like you see, there is no second argument. So everything is done in the computational basis. Given a state in any basis, you can transform it in any other basis. For example, like, let's generate like, a pure random state in computational basis. Let's call it whatever we want to call it, state, psi, whatever, like, the notation is not important.
Just trying to organize it a little bit better.
Random pure. Now, like, what's happening here, like, this time, like, we specified that in that very, like, basis. So this time, like, for example, let's look at the formula. You see, this time, like, the formula is given in Pauli X. So, like, this is one interesting feature that you have, like, this basis transformation. It's a very nifty feature of our framework. So both for basically any quantum object, you can easily transform it from one basis to another basis. Just make sure that those bases is representing the same Hilbert space. So here, like, remember the first argument that specifies what type of state, and then the second argument tells you what basis. Here, the basis is Pauli X. Uh,
I just
we
wanna, can I just comment? Because I was showing this yesterday, and it's important to distinguish two different cases. When you create a state in some basis like this one, when you provide an amplitude or name, right? It's gonna just treat those amplitudes or whatever formal state you have in this particular basis, or you would actually convert it from computational basis to this basis. This is like a different thing.
Yeah. So like the last example that Nick is showing, you are creating a state in computational basis, and then you transform it into Pauli X basis. So it's basically a basis transformation. Remember, like, these two states are the same. Like, it's just like, in which basis you would like to see your state.
All right.
Okay. So the next examples, like, they are like, trivial. Like, we can just leave it to our users. It's just like, creating a state and the transformation. Let's go with the composite one, which is a Bell state. So remember that, like, those, you can do that. Now let's go with the Bell state. So now for the Bell state, how we can do that. So like, you see here we have a very particular superposition of, phi plus, phi minus. Now, how we can create them, you can either go to Bell basis and give an amplitude, for example, like, any amplitude. I don't know, let's go with symbolic amplitude, A, B, C, D. Let's add the other two, so just show them all of them together. So you see, like, this is the Bell state, and like, each one corresponds to particular, like, Bell state that we have. So when you want to create that particular superposition, you just need to specify the corresponding amplitude. So it's phi plus, so we are going to put phi plus 1 over square root of 3, and likewise for psi negative. So basically it's going to be D and A. So
So it's 0, 0.
yep, that one going to be negative square root of 2. There's a negative sign.
Oh,
Yeah. So that's the state that we created. So that's one approach. Like, in this approach, what we did, we use a given name basis. Okay. Of course, another approach is literally creating that superposition using name state, because we have a quantum state 5 plus. So we can start by creating your quantum state 5 plus. Again, this time we are using name states 5 plus, and then this is the definition of 5 plus, and then you can create a superposition. Now let's transform it into Bell state. That's the representation in Bell state. uh, and then what you can do, you can create psi minus. That's psi minus, and then for the superposition is literally adding them together with the corresponding coefficients that we have there. So there are different ways of creating a quantum superposition, and these two these two states are exactly the same thing. So please keep that in mind, whichever way you feel more comfortable, so just go with that. Sometimes people, they prefer the amplitude, but when you are using the amplitude, you should know which amplitude corresponds to what basis, or you can go with the summation of some quantum states. Okay. And Nick already showed you the formulas and everything. So the second part of that question, which was about the formulas, we already addressed that. 2 over square root of 3. There's just a typo there.
Just showing off a little bit of nice notation.
So what you see here, the traditional form, remember, on Mac is Command Shift T. It's just, you just need to evaluate that, and then Command Shift T, it shows you the corresponding formulas. Okay. Now let's the next step, we are doing some simple operation that we can do our state. So we created that superposition. This time we want to trace out the second system. So the function to do that is quantum partial trace. So that's our state. Remember, it's in 2 dimension, it's a composite system. So we just take quantum partial trace. So the first argument is the state. The second argument is the system that you want to do the partial tracing.
Oh, we can't do that because it's a 4-dimensional one.
Oh, then let's go with transform it into computational basis. Let's go to 2 by 2.
Oh, yeah.
So just let's clarify what happened there. So you can define your Bell state in a big system of 4 dimension and say that look, this is my system, it's 4 dimension. So physically it means you have only one single quantum system, or you can break it into 2 subsystems. You can say that look, what is happening in reality is it is 2 qubits together. It's a composite system. But in our framework, we understand them, and then the next step, after partial tracing, of course we know that it's a mixed state, but we are just checking that whenever we do the partial tracing on the top of pure state, we are going to get a mixed state. Now, what we can do, for example, let's call that after partial tracing, whatever is that state, let's call it, I don't know, let's call it R, for example. One interesting feature, remember, it's a mixed state, so we can purify our states. So purification is a very common process, in quantum information. So the syntax is just purify that. So what's happening here is that we are using an ancillary quantum system. We go to a higher dimension, and in this higher dimension, your state is basically pure. Now, if you want to recover the original state, so if you want to recover that, you just need to do the partial tracing over the ancillary qubit. So let's just take the partial trace of the second one. You are going to recover your mixed state, and you can easily test that that's exactly the same as the original mixed state R that we started with. Okay, so it's just the purification, it's a very common process that we have in quantum information. So in order to purify a mixed state, just add, ask for the property purify. Of course, like, if your state is originally pure, if you purify that, it's not going to change anything. So remember, purification is always means going into a higher dimension. Okay, going into a higher dimension. Okay.
We're still gonna go into higher dimension. Just
Yeah, those amplitudes are basically, it's a trivial process. Let's put it in this way.
yeah.
I don't know, like, just quick comment. Remember, like, when you purify, when you go to a higher dimension, the amplitudes, they are basically the square root of, like, the amplitudes that we have in the mixed state. Therefore, there are some cases that, people are interested to go into a higher dimension without changing the element of your density matrix. So one more time, like, for example, Nick, let's, create, I don't know, let's go with symbolic, mixed state, like let's call it A, B, C, D. And let's purify that. I know it's unknown because, like, it's not clear it's mixed or not. And let's look at the formulas. You see here, like, we are going into higher dimension, and then, like, the relationship is not directly the relationship that we had with those parameters. So that's the purification. We have something similar to purification. We call it bent. So bent, what's happened is that we literally just expand the dimension without changing the amplitudes. So this time, for example, let's look at the formulas. You see here, like, it's expansion without changing the amplitudes. Again, like, this is not the usual purification that we have in quantum. So that's not the case. Remember that, like, it's not the same thing. Like, for example, take the quantum partial trace on the second quantum system. This is not the original state. That's what I'm telling you. Like, it's like, there are some extra factors there. Okay, you see, like, it's not the same thing. So that's the whole idea, like, behind, like, let's look at the form. So you see, it's not the same thing. So just one comment. Remember, like, bend is very similar to purify, but, it's different. So we try to provide all, details in our documentation. Okay, so let's move on to the next example. Traditional form. Two random mixed state in 2 dimension calculate their, burst distance, which is a very particular metric for the distance. So how does transform? Okay, Miguel, like, I know, like, this is a common question that we got from many, students. So Nick, let's show it one more time. Let's create a quantum state.
This one.
Yes. So remember, that's what we call, like, the object is quantum state that has that summary box with some interesting information. If you want to see, like, the usual formulas, it's just a traditional form of that. So you can directly ask for the traditional form, or on, the shortcut is Command Shift T. So that's how you can look at the traditional form. Okay. So, lucky us, like, this case, like, it turned out to be 0. But anyhow, like, quantum distance is the function that you can use for, measuring the distance between 2 quantum states. And, we are supporting, like, let's see, I guess, if I remember, let me just take a look at that. The measures that we have are fidelity, trace, spurious angles, Hilbert-Schmidt distance, Bloch, and relative entropy. So these are, different measures that you can use in order to calculate the distance between the two. If not given, if you do not specify, like, what metric, automatically we are going to use fidelity. So like, when it's not given, no argument there, like, it's going to be fidelity. So that's one way of like, doing the calculation for, and by the way, like, because it's a random, generation at each step, like, those are different. Okay. I think like, so far, like, everything was kind of, easy. Now let's make it, more complicated, like, some
All right.
fancy topic. Okay. So let's see. What is a Werner state? Werner state. So, what we usually call as a Werner state, it's a very particular quantum state. It can be written as a convex combination of, one of the Bell states and a maximally like, mixed state. It is usually defined in a given dimension for a given probability function. What is special about Werner states is that when you have a tensor product of two unitaries, your state is basically invariant under those unitary transformation. So that is what's special about Werner states. Okay, so what we have here is a Werner state in dimension 2 and with the corresponding probability. So let's see, let's look at the question. The question is telling us that, for example, let us show that, let's go with a probability p, I don't know, let's give it a value. So it's more than 1/2. So you see, it's not entangled. It is separable. When it's, less than 1/2, it's an entangled state. So that's an interesting feature for Werner state. How we can check just to see like how we can check that. For that Werner state, we can directly ask for the corresponding eigenvalues of the density matrix. For example, let's look at the eigenvalues for the density matrix. So as you can see, like, in this case, when it is entangled, all of them are positive. And let's look at, the case that is, separable, like, more than that.
There is.
Interesting. Oh, sorry. I forgot. My bad. We should take the, I totally forgot. Take the partial transpose. So I totally forgot, like, the PTT criterion is for partial transpose. So let's take the partial transpose of the second system. So it's going to be the transpose of the second system. And then let's look at the eigenvalues. And there, one of them at least, That's,
not what it's actually doing.
let's look at, what, just a second. When P is less than that. Okay, let's give it like, let's give just, oh, you are not specifying like, Nick, you're not specifying the dimension, but dimension is set automatically as 2.
I think so.
Yeah, it should, let's give it 2. It should be exactly the same.
Nothing changes.
Yep. Okay, so this is a an issue that we need. So let's give it P. Let's go with the generic P. Let's see what happens with P. If we cannot reproduce it with P, it means like okay, that's transpose. We are doing the partial transpose. We are looking at the density matrix. Now all of them are positive. Okay, so that's just like, a bug that we will take care of that. As I said, yes, Douglas, like, it's a convex of, Bell state and, maximally pure. One of them is a probability, the other one minus that
Use a
probability.
negative eigenvalue.
Yeah, one of them is negative, but why we don't see it, like, when we ask directly for, that's a
Well,
strange.
it's supposed to be, it's the one here.
This one, like, should be all of them should be positive, negative. Okay. One at least negative. So why we don't, what happened? Like, why we didn't see it in the previous case?
Not because it was different. What you can do, this is the entangled case. This is not entangled.
Yes, that's what I expected. So did we see this output from the very beginning? Okay, so maybe like we were confused. Anyhow, like I just wanted to say that when it is entangled, one of them is definitely negative. That's exactly the case that we have there. By the way, it's not like it's a one-way
That other way
relationship.
around.
Yeah, it's one-way relate. Yeah, that was the part that I guess like that we were confused. So if it is separable, then all of the eigenstates are non-negative. If it is entangled, it is guaranteed that at least one of them is negative, at least one of them, which is what we are showing here. It's not the other way around. Like, one more time, guys, remember, like, it's not a sufficient condition. So you cannot go the reverse. Like, you cannot say that, like, okay, this is a criterion that I can use to say if it is an entangled state or not. It works. It is a necessary and sufficient condition when the dimension is 2 and 3, but when you go to a higher dimension, it's not enough. And actually, just since we have quantum entangled Q, like for quantum entangled Q, we are using the realignment, which is the most generic criterion to have separable like quantum states. So initially in our design, we went with we were using like PTT criterion, but since it was only for qubits, we just dropped that. Okay, so for a second, like, I was like, is it a bug? Because I literally checked it, before the presentation and everything was okay.
Or we can't specify. I guess we can't specify. Which criteria are we using? I don't remember.
I don't think we have that option. For quantum entangled monotone, we have that option. So you can just ask, yeah. So for quantum entangled monotone, you can use different measures to calculate the entanglement. So you can go with the concurrence, you can go with the Rayleigh entropy. Realignment is like, one of the most interesting ones that tells you like, what's happening in, for if it's like, so that's the default one. Yeah. Okay. So, let's move on. Next example, like, Schmidt decomposition. That's a very nifty feature when you are going to the higher dimension, because it helps you to do like, lots of calculations. For example, like, let's create that, superposition. And this time, let's just go with the amplitude because it's the same order. So we can go with.
All right, so what is the
1 square root of 2 negative square root of 2.
1 over square root of 3 or something?
Yep. And the last one is a negative of that. So that's our quantum state. And, as you can see, it's not, in the form of like, Schmidt decomposition. So let's ask for the Schmidt decomposition, which is Schmidt basis. Basically here, like, we are just changing the basis. Remember, a Schmidt decomposition is nothing but like, a change. So let's look at the formulas, like, people, they can see the formula. So you see now, it's like, 1 and 1, and then 2 and 2. So in case if somebody is interested, like, those, Schmidt bases, like, we can extract the basis in case, like, let's ask for the, after a Schmidt basis, let's also look at the basis. Yep. And let's look at the association for the. So these are basically like, what's happening, behind the scene. Like, this is a transformation that you can do. And in this new basis, you have that very particular form, which is a summation of like, UI, VI, and then like, you're doing, summation over all of them. So that's basically the idea of like, Schmidt decomposition. And the last example for today, and then we would move on to the next topic. I think like, let's do bipartition is also a very interesting feature. I know you briefly commented on that yesterday, but let's show them, one more time. Like, let's have like W state of 4 qubits. So the dimension is 2 to 4 16. So that's basically a uniform, like it's kind of like it's not a uniform superposition, but you have a uniform superposition, and that like you count all the permutation of one and the rest are zero. Now the idea of bipartition, remember, it's a quantum state containing 4 subsystems. Bipartition means make it like 2 particles, 2 subsystems. So if you do not give any argument for bipartition the way that Nick is doing it there, what we do behind the scene, we take the dimension of the first subsystem and then combine the rest as the second subsystem. So that's what's happening here. Now, you may say that, look, I would like to have my bipartitioning to be like this. I would like to combine the first 2 together, and then the third one and the fourth one, let's call it another quantum system. So this time, like, we are just collecting subsystem 1 and 2 together, and we are going to form a new one. So it can be done in 2 ways. First, you can say which one of the 2 you want to combine, or if you have the information about the dimension, you can say that, look, the first one, the dimension is 1. So just give me the dimension of that very particular state. You see here is 4 and 4, then the next one is also 4 and 4. And you have absolute freedom. You can here go with say that, look, I would like my first system to have the dimension 8. So you can go with like, 8 and 2. So like, this time, the bipartitioning is done like, and the new system is 8 and 2. One more time. Physically, these quantum states are completely different. Okay, we know that like it's like depending on the number of subsystems, the actual physical system is different, but mathematically all of these states are the same. When you do the bipartitioning, like I guess Nick showed in one case, with bipartition or without the bipartition, all of them are the same. So bipartitioning is a very interesting trick. Remember that the most important thing would be the how should I call it? Like you can do Schmidt decomposition. Remember, Schmidt decomposition you cannot do it like when you have more subsystems. There is one question: is partial transpose is the same as quantum partial transpose? No, they are not the same thing. Like it's when just Nick, show one example, like generate one 2 by 2 pure state. So I don't know, call it whatever. And then when you do partial transpose, like for example, let's do the partial transpose on the second one. It's a fancy process that we do, but at least look at the dimension. It's still a system of 2 subsystem, and the dimension is the same. But when you do partial tracing, like quantum partial trace, so if you do the quantum partial trace, like with quantum partial trace, you are basically tracing out one of them and you are reducing the dimension. So that's the difference between the two. But like transpose with some argument, it's like what we usually call as partial transpose. Again, it has exactly the same definition as partial transpose that we have for all the matrices. That's the same thing. Okay, so let's move on to the new topic, quantum operators. So there are a couple of interesting examples there, but I think like it's better to move on to the next topic, quantum operators. We already discussed about many of them, so we can go through that very fast. Like we go with the named operators. Like we have a collection of named operators. One interesting feature are control operators. Many of named control operators is like they have C at the beginning. Okay, so like so you see like this is a circuit diagram. The control order is 1, the target order is 2. So like that's how we can get it. uh, before we move on, let's just pause for a second. There is a question: why von Neumann entropy complex? Miguel, I believe you are using a case where your system is not actually a density matrix. I guess you are using one of those cases, like this case, unknown state. Look at that. It is not an actual, density matrix. So this, if you show it to, like, Nick, show the actual the density matrix.
It's just not physical.
Yep, it's not what we call, and ask for semi. What was that? The feature semi-definite.
Semi
Definite.
positive
Positive semi-definite. Yeah. So you see, it's not positive semi-definite, so it doesn't represent an actual quantum state, and that's why the entropy is complex.
Yeah, maybe if you ask for probability, probabilities actually can be normal, which is interesting.
So, like, remember, like, in our framework, like, there are lots of things that we can, like, when you generalize that, like, when you go, for example, to categorical quantum theory, when you go ZX formalism, like, you can go to some very generic states and you can do all your computation. Not only that, by the way, many of, like, issues regarding the entanglement, if quantum states are separable or not, you do some fancy mathematical operation, like, partial tracing, partial transposing, and etc. And those are not always an actual physical processes, like what the example that we just showed you here. And you see here, like, one of the eigenvalues is negative when you do the partial tracing. So that's why it is not an actual, or that's not a physical quantum state. That's how we can see it.
I don't remember what probabilities are this way.
Eigenvalues, like, it must be always positive. I guess, the probabilities are always positive even in that case.
But for the density matrix, I think probability should have been determined by eigenvalues. So I was expecting some.
Oh yeah.
Some weird probability.
That's another,
so I'm not sure what's here. Why it's this probabilities here. Anyway.
Are they normalized? It's, yep, I guess they are. Yep.
Yeah, because maybe after normalizing eigenvalues, that's what you get.
Mm-hmm.
Right? That's how it's computed.
Normalized by total. You forgot S.
No.
No, that's interesting. Maybe we have to generalize, our definition for probabilities out of a density matrix at the condition if they're physical or not.
Yeah, I remember changing it recently. Maybe I screwed something up again.
Okay, one homework for us. But good observation, Miguel. Yeah. So, and that's one thing that you guys have to remember, like, whenever you're doing, fancy operation, make sure that your state is actual, a real physical state. Otherwise, like, many of your measures is going to be a strange measure. So, for example, a very common mistake that I have seen by many people when they are generating, like, random states. For random states, like, they just use, random complex as a function. But remember, random complex does not give you, like, a positive semi-definite matrix. So some of your examples cannot be an actual physical states. There are some tricks to address that. So
Something different. I don't quite remember how it's determined. Yeah, maybe
we'll take care of that.
Yeah.
Okay, so, like, one of the many things, like, when you are working with any operator, like, they, like the example that we have here for permutation, since, it's a cycle, many of you maybe, like, you are not like, how the cycle works, like, one by one, and then, like, the last one is also, permuting the first one. So we can always look into the corresponding circuit diagram. Okay, for example, for that operator, the permutation operator, either you can directly ask for the circuit diagram, which is the property of that operator, or you can wrap it around like quantum circuit operator and ask for the diagram. So like there are either ask for the circuit diagram, which is what you see, or wrap it around circuit operator and ask for the diagram. Both gives you the same thing. And now like you can see like how the permutation works. Like the first one will be the third one, the second one goes as the first one, the third one goes to the second one.
No, basically you can read it as a cycle. It's what
Yep,
it's right.
that's
One
why
goes
it's
to
called cycle.
three, three goes to two, and you rotate back, and two
Two
goes to
goes
one.
to the first. Last one always goes to the first one. Another trick that I use personally, like I also put it there, like another way of visualizing the permutation, because permutation is a big deal for some circuit designs. We will discuss it like tomorrow and the day after tomorrow. Another trick for visualization is just apply permute on like order list. That's the next example that yeah, that we have. Yeah, you see here, like if you apply that, you would understand that okay, that cycle, look, it's replacing step by step. So that's how you can visualize that.
It's just don't confuse it with this.
Yeah, those two are different. Yeah. Okay, so we discuss about like yeah, permutation sometimes it can be confusing, but there are lots of other functionalities in Wolfram language that you can use to have a better understanding of permutation. I usually use circuit diagram, but again, like you guys can use. And remember, the cycles, they can be very fancy. Here we are just giving a list of qubits. You can give a list of the list, so like it can be very complicated. Uh, Remember to use order. Order makes your life easy whenever you are constructing the operator. Like we understand behind the scene, we understand like where we need to do quantum tensor product, like the example that you see here. Like instead of like making like a composition, the order understands that. That's exactly the same like 10 quantum tensor product. Like you can write down the tensor product if you like. uh, of course, this case, because they are one and two, they are kind of trivial. But if it's not like always adjacent, like you're gonna have a very hard time if you want to construct it manually, like 100. Okay, so it will be difficult. Like just imagine like how many qubits that you have to add. It's gonna be a big one. You added 100. So you see
Yeah,
x on the first one and then x on the 100 qubit. So see how easy you can construct it using, at least give it 10 so they can see it, huh?
I think it's fine.
Yeah, you see here, like only the first and the last one it has a label. Okay, so order, like remember, like whenever working with anything order, that's the key things for the operators that you have to pay attention. It helps you a lot. Let's move on. Like the operations that you can do on the top of operators, literally everything. Like there we are taking an exponential given an angle. So you all know that this is how we define rotation along like x-axis. And of course we also have rotation. Which one you want to use, again, like case by case, like it could be different. Some operations, like there are different ways of like implementing them. Like look, here we are adding square root on the top of your quantum operator, or you can use the building operator sx. We also have v, if I'm not mistaken. V represents the same operator, right?
Mm,
uh, if I, because that's another common notation that people use in the literature for yeah, the square root of like not, or literally you can add it on the name of that operator. So these things are all the same. So like which one you want to use, it depends how readable you want to have your code. uh, so
that's more cool.
uh, regarding addition, subtraction, the same story. And you are going to see some examples, especially when we discuss about like Ising type of interactions. Like you can literally add the named operators, which is exactly the same as like adding, creating each operator separately, and then add them up. Like, the examples that you see here is a summation of t and x. You can literally add them up. So that's another way. You can go fancier. You can say like, some sort of, coupling. And of course, that's the same thing. Create them separately and then add them up. It doesn't change anything. What's the interesting part are generic rotation operator. So the generic rotation operator is like, given a coupling constant here, it's represented by theta, you can have a composite quantum operator and you can create the corresponding exponential. Remember, the exponentials in this case, they are exactly the same like when you have time independent operator, they represent time evolution operator. Why they are interesting? Because there are some cases like this case, if you just evaluate that. Okay, it is interesting because we are adding bunch of operators x, x, y, y, z, z, and their exponential is also separable. We can write it down as multiplication of different exponential terms. But remember, this is not always true. That's true only if those operators are commuting. And most of the time it's not the case. So you really need to be very careful when you are working like with this uh, type of operations. That's why I always go with the top one, because either they commute, or if you are not sure, just go with the top construct. So when the exponential multiplication is a big deal, that's why we also added Trotter Suzuki decomposition for approximating some time evolution. We will discuss about that very soon. Let's look at some Ising modeling. Here, what we are doing here, we are specifying where each operator is acting. So it's like, first we would say XX between qubit number 1 and number 2, and then 2 2 between qubit number 2 and number 3. So Miguel, are you asking about this very specific example or the previous one? Oh, sorry, Nick, there's a typo there. In the explanation, I just multiply them. It's exponential a plus b plus c. They're below that in my explanation. Yeah.
Well, here.
Yeah, it's in the first, yeah, it's plus. Thanks, Miguel. Good catch. Yeah. It's summation, and then it's translated as multiplication if they commute. Okay, so for the Ising model, you see here, you just need to specify the order. So, Nick, do you know any simpler version of showing Ising coupling? Is it I think that's the simplest way of showing the Ising coupling.
Yeah.
I
Seems
don't
like
think you can simplify it further.
oh,
No,
you're not
you don't need
sure
that
this
one.
one,
Yeah,
try this one.
yeah. The first one, remember, whenever the first one is not given behind the scene, we would treat it by default as the first and the second one. And of course, you can increase it. You can go 3 and 4, whatever is the length of your chain. You can just increase it. Like 4 and 3 and 4. Yeah. Okay. By the way, in this very special case, as you see, all of them, they have the same coupling. Okay. Uh, uh, if different coupling, so then it's, you just need to go with a different way of implementing that. So change that interaction term, that coupling term. Okay. Another the interest, so when you are working with the operators, remember, rotation, generic rotation, it's one big construct that makes creating operator easy. Another big construct is our conditional operators. So for conditional operators, you can have control 0, you can have control 1, you can have a collection of operators acting on your target qubits. And let's just look at the diagram, so you see here we are saying x acts on 1, y acts on 3 if control 1 is 2, control 0 are 4 and 0. So it means if 2 is 1, 4 and 5 are 0, we are applying x and y on qubit number 1 and qubit number 3. So it's a very neat, basically construct for our control operators. And of course, circuit diagram, like, it gives you exactly the same thing. Now, just, since we discussed about, like, Ising coupling, let us consider, like, a chain of, 5 qubits interacting through, Ising interaction. Now, like, the headache of dealing with time evolution is that, like, in our framework, we can easily deal with, any time evolution. Okay, it's easy for us, we can compute it, exactly. But it doesn't mean, like, there is a circuit out there representing the same thing. Okay, the biggest challenge is that what is the circuit resembling the time evolution of an operator or a collection of operators? Okay, so the Suzuki trotter, the composition, it helps you to construct a circuit mimicking, the time evolution. Whenever you are doing that, remember, like, there are two important, inputs here: the collection of operators describing the time evolution, and then next, at what order, like, to what order, like, you would like to have your approximation, because Trotter Suzuki, like, it's an approximation to actual time evolution. And for each order, how many steps? So here we are just going, with the step 1. I think if we go with the step 2, like, it's going to be a huge, it's going to take time to,
It'll be twice as that.
yeah, you
Just
see.
the same thing repeated twice.
Yep. So this is, like, how we can, in case, let's just also show the labels, like, maybe those of you who know, like, the next one. Oh, too complicated. So show the label at the, there's a piece of code. Yeah, that's uh
That's because it's a two ordered now. It's a
oh, okay, now
stable
it's not
case
mine.
for
Yep,
those.
yep, 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 yep.
Have to flatten it.
Yes. And you see, those of you who are familiar with the Trotter Suzuki decomposition, those are exactly the terms that we have when we do that particular decomposition. But again, like, if you are not representing your time evolution by a circuit, don't bother. Just go with, like, the time evolution that we have building in our framework, and everything can be computed exactly. But if you want to look at, like, an actual, like, circuit resembling your time evolution, that's how you can do it. And look at here, the first term applies on the qubit number 1, number 2, number 3 to, like, the usual coupling that we have in Ising model. And I wonder, like, if Nick had time last time to comment on, like, the tensor flow that we have behind the scene. For us is always, like, tensor juggling. Remember what we call as an operator, the fundamental difference between operator and a circ and a, let's see, you are showing the tensor. So, okay, that's exactly, like, so maybe that's too complicated. So, maybe it's vertexes, you want none. So basically, like, this is a graph representation of, can we also show, like, with the indexes, like, what was the function? Tensor network index. Yep. It's gonna take time. Maybe that's way too big. So Miguel, like, one way of, okay, now we have it. One way of, like, understanding, like, so here, the way that we understand, like, this is a completely different metadata to understand the circuit. So here, we are understanding everything in terms of, like, bunch of, tensors, and each tensor, like, what we do in each step is, like, basically, contraction, and, playing with the indexes, resembling exactly, like, the type of evolution, stepwise evolution that we have with the usual gates. Okay. uh, when we discuss about, like, Nick also evaluate the last code. Let's just show them, like, when we discuss about an operator, what do we have here? Look here, this is an operator acting on two systems. So in our TensorFlow, like, here we have two input, two output. maybe it's interesting if we just show a quantum state, just showing that, look, fundamental difference with the quantum tensor dimensions. So that's what's happening behind the scene. And if we show like, a quantum state just for the sake of difference, and let's look at the diagram, like, to see like, there's no input when we switch to quantum state.
Well, it's gonna be input because it's the same map. Or you want a different state?
Oh, different state, not exactly the same. Yeah. So like, behind the scene, like, the fundamental difference is that those of you, I guess, that was the textbook that Nick mentioned, like, so in this type of like, approach for us, like, quantum state is the one with no input. So input, and I guess, they can also, we have the property input, input, what was that? Input,
What
qubit? Was it input qubit? Oh yeah, you see 0 qubit. Yeah. Input, and then let's ask for the output. I guess, the outputs, it's output qubits. Okay, and then output, it's gonna be 2. Yeah. So all these, tensor features, like, it's also in the long property list of our quantum states. As of now, they are not well documented. Hopefully, like, we would document them better, but our understanding was that, people using our framework, most of them, they don't care that much about those tensor features, unless you want to do fancy circuit optimization, and you would care about the tensor network, and like, it is available, so you can easily just call the, like the 2 examples that Nick showed, like, you can look at the tensor network of a circuit, and whatever optimization you want to do, you can do it on the top of that. Okay, oddly enough, I felt like, we are gonna run out of time badly, but not bad. So at least, we managed to cover the most important topics. So next time we are gonna do more problem solving. By the way, give it a try. Try to solve those problems, yourself, and then, we would move on, to the next topic. Especially the last examples when we have the circuit diagrams, like, the main reason that we are basically pushing you guys to do some sort of, practice on these topics is that the more you know about quantum state and quantum operators, the better you can design a circuit for a very particular, goal. Like, then quantum algorithm development would be much easier for you. Uh, Sadly nowadays, like, whenever you guys, like, look at, different trainings on quantum computing, most trainings, they directly jump to quantum circuit without emphasizing how important is the operator design, how important is, like, what's happening to the quantum state, and fancy interesting features that you can extract out of quantum states. So I know you may not like it, but trust us, try to struggle a little bit with our quantum state features, quantum operator features, because once you master those, features, working with quantum circuit operator will be much, much easier. So next time, like, we are gonna review, like, some of these examples. You are gonna have a, like, better understanding. But today, give it a try. So you would be ready for tomorrow, like, to see, like, how these examples can be easily constructed, like, in our framework. And by the way, all of these examples, like, on purpose, like, those of you who are familiar with this field, like, you may know many of them, like, these are the most common gates operators that people use when it comes to circuit design. Okay, we are on time. Any comment, any more question? Nick, do you have any input, any comment you would like to add regarding quantum operators?
Quantum operators in particular.
Mm-hmm.
Well, just see, maybe we just forgot some nice property. Or maybe it's connection to the, well, maybe operator state duality is important thing to know about. I already briefly showed it here,
Mm-hmm.
right?
Yep.
When you can convert it operator into a state. It's
Mm-hmm.
basically, maybe it's important to know that underneath each operator is actually what we call technically a state, but it's a little bit of cheating because it's not a state, but it only
That's why we call it pure map.
states in our framework can also represent a map in general. So
Mhm.
underneath each operator there is a map. It's just not a map that specifying not order, without order. So you can think of operators as maps with some order on top of it. So you can put it in the diagram whenever you want,
Yep.
wherever you want. But states, a pure state or pure map is just a thing with inputs and outputs without any particular order attached to a circuit.
Mhm.
So
So basically, like, when you, in terms of metadata, like, the most important thing that you have to remember about, like, an operator is the concept of order. Because in the usual quantum mechanic, when we write down, like, the operators, for example, like, we write down bracket, and, like, everything has kind of, has state representation. Okay. In our framework, you can do that, but the price that you have to pay is losing that piece of information about the order. So that's why, like, we would like you guys to see them, like, differently. And, like, the usual notation, bracket notation that you have in quantum mechanic, on purpose we call it a quantum state, but it's a mapping. That's why it is called pure map. So I know it, it's confusing, but there has been lots of discussions, behind the scene when we were designing that. Mike had a comment, like, Nick, regarding, like, the palette is not, they cannot see it. Like, can you comment on that error with the palettes that some students may?
well, sometimes I don't know why. If you uninstalled the Packlet, like using Packlet uninstall for some reason, or use some code that using it, you don't have to use it anymore, right? Just installing over the Packlet that you currently already have should be all right. But if you uninstalled it in the current session, Packlet, this palette sometimes is not appearing correctly, so you have to restart the whole desktop or your front end in order for it to
Yeah.
appear.
As of now, Mike, we believe it's a bug in our front end, but we are not 100% sure. We are working on that. But if sadly, if you observe this issue, you just need to basically, close and open your desktop and install, like, the packlet, and then it should pop up.
No, it should pop up immediately, I think. If you uninstall the Packlet and it's not there, restart the desktop, it should appear immediately.
So it happened to me. Like, it's not only you, Mike. Like, I guess yesterday or the day before yesterday, me and Nick, we had this discussion. So
Yeah.
we
The whole
do
deal
not
with
know.
Packlets is pretty new, so technically it's still under development. So
Yeah. And there might be, again, as we said, some bugs related to other things, and we do not know. But hopefully, we can resolve this issue very fast. Any other question? Any other comment? Any gray area? So please let us know, like, we really would like to hear your side, like, how would you like to use our framework? And we would focus more on that. So uh, this time, as I said, what we did different, we gave you the big picture. You remember we started with the circuit, and now step by step, like, we are, like, giving you more taste of, each functionality. Okay, so Mark, like, me will he's responding. So I think, like, I also got your email. Hopefully we can help you to resolve that issue 100%. So I think it's a good point. We could wrap up our session. Thanks everyone. Looking forward to our next meeting, which will be tomorrow.